We're going to do a little bit more with implicit differentiation today. First question is just more of what we did yesterday. So it says find dy dx if our equation is x squared minus the cotangent of x over y is equal to 4. So I don't see anything that's obvious to simplify. I mean, if you see something that, will make it simpler, then I would go ahead and do that, but I think we're going to leave it alone. So the derivative of x squared is 2x minus, and we have a chain rule here. The derivative of cotangent is negative cosecant squared. So I had a minus, but then we're subtracting a negative. Then the chain rule says we need to multiply by the derivative of the inside. Well, the inside is a quotient, so we're going to use the quotient rule. I'm going to square the bottom, rewrite the bottom, multiply by the derivative of the top, minus the top times the derivative of the bottom, which is called dy dx. And I go to the other side of the equal sign, and the derivative of 4 is 0. So we've taken the derivative of everything. Our goal now is to get dy dx by itself. We want to just kind of talk this through. I mean, we really have two terms, right? This one thing is all one term, and here's my dy dx. So I would start by moving the 2x to the other side. So we have cosecant squared of x over y times y minus x dy dx all over y squared is equal to negative 2x. This dy dx is in this fraction, so let's move this guy. Let's divide by cosecant squared of x over y. Now, I mean, it's up to you what you do at this point or how you kind of deal with this, but dividing by cosecant squared is the same as multiplying by sine squared, so I think I'm going to do that. I'm also going to multiply both sides by y squared. So I have y minus x dy dx equals, I have negative 2x times y squared. And again, you can leave it as divided by cosecant squared. I'm kind of looking ahead thinking I'm not going to love that. So I just changed that into sine squared. Clearly I didn't leave us enough room to finish this, but the last thing we're going to do, subtract the y and then divide by negative x. So we have dy dx equals negative 2xy squared sine squared of x over y minus y all over negative x. So there's nothing different in here from what we did yesterday. It was just a good little reminder of looking for the order in which you're going to move things around. So just be careful. I would start by asking how many terms do you have and how many of them contain a dy dx, and then start moving everything away. Okay. All right. This is a little bit different than what we were doing yesterday. It says find the value of the second derivative at the point when x is 1 and y is negative 3 on this curve right here. So we know from our work with derivatives that if you want to find the second derivative, you need to find the first derivative. So we're going to find dy dx. Then we're going to take the derivative of that. To get the second derivative. And then we're going to go plug in our x equals 1 and our y equals negative 3. Okay. All right, so here we go. Let's find some derivatives. The derivative of y squared is 2y dy dx minus 2x equals, whether you distribute that 2 or not, the derivative of the right-hand side will be 2. So let's move the 2x over, and we'll divide by 2y. So I have 2 plus 2x all over 2y. My suggestion, if we're going to take the derivative again, is let's take out all those 2's. So I have dy dx equals 1 plus x over y. So there's our first derivative. All right, so we are ready to take the derivative of the derivative. So let's come over here. I'm going to take the derivative of the first derivative, which is the second derivative, right? If this was y prime, its derivative would be y double prime. So the derivative of dy dx is the second derivative. And then on the other side, we're going to use the quotient rule. So we're going to square the bottom, rewrite the bottom, multiply by the derivative of the top, minus the top, which is 1 plus x, times the derivative of the bottom, which is dy dx. So at this point, we've found we've found the second derivative. It is already by itself. The second derivative equals. The only problem is that it doesn't just have x's and y's in it, it also has dy dx's in it. Seemingly a problem, but not so much, because we know what dy dx is. Well, let's go fill it in. So I have the second derivative equals y minus 1 plus x times 1 plus x over y all over y squared. So this right here is my second derivative in terms of x in y. So now we can go find that value. So I didn't want to say the second derivative equals because we're changing it, but I'm going to say we're going to plug in. So I have negative 3 minus 2 times 2 over negative 3 all over negative 3 squared. And technically that we could be done. I mean, we can clean it up. We have, let's see, negative 3 plus 4 thirds all over 9. I don't know, so we could multiply everything by 3. So we have negative 9 plus 4 is negative 5 all over 27. And there it is. Okay. So this last question here is all together. It's like a part A and a part B. And it says we're going to need a calculator, so I'm going to grab mine. We've got a lot going on just in even the givens. So it says the graph of the equation, x squared, blah, blah, is shown in the graph here for y less than or equal to 11. So they're just saying they stopped at 11. It is also known that the derivative is equal to this. Ooh, well, that's nice. They gave us the derivative. The x-coordinate of point P shown on the graph is 2. So we know the x-coordinate here is 2. That's all we know so far. All right, so here we go. Part A says, write an equation for the line tangent to the graph at point P. All right, well, we want to write the equation of a tangent line. We need a point, which we already know the x-coordinate, and we need a slope. And we know slope comes from the derivative, and we already have the derivative. Too bad the derivative is in terms of x and y, because we could have found the slope right away, but apparently we're going to need the y-coordinate first. So we've done some questions like this. If we want the y-coordinate, we're going to go plug in our x into our equation. So I have 2 squared equals negative 2 plus y plus 5 cosine of y. Or I have 4 equals negative 2 plus y plus 5 cosine of y. I want to solve for y. Which, by the way, when you look at this graph, when x equals 2, there are actually 3 different values of y. So we want the one that looks like it's close to, like, say 5. Okay, so just kind of keep that in mind. I'm going to use the solver because I kind of know how many answers I should get. I mean, we should get 1, and it should be close to 5. So I'm just going to go grab my calculator and hit menu, number 3, number 1, and I'm going to go type in 4 equals negative 2 plus y plus 5 cosine of y, comma, y. And there's my y-coordinate, 4.928. Now, that's a rounded value, so we'll be very careful with that. And when we go use it for the slope, I'm going to use the exact value. In fact, I'm going to go take care of that right now. Let's take this number and store it. So my store is right above my variable. So I'm going to hit Control Variable, take that answer and store it for some number A. Reason I'm doing that is so that when I use that number to find the slope, it's going to be as accurate as it can be. All right, so we have our point. Let's go find our slope. They gave us a formula for that. M equals 2 times the x-coordinate of 2 divided by 1 minus 5 times the sine of the y-coordinate, which is 4.928. But don't forget, we're going to use A, right? So I'm going to go back to my calculator and type that in. So I have the fraction of 4 over 1 minus 5 times the sine of A. And when I type in my A, it's bold, and that's the calculator's way of saying you have something stored there. And if I'm truncating, I get 0.679. So now I have my point, I have my slope, and we're going to write the equation of that tangent line in point-slope form. So I have y minus 4.928 equals 0.679 times x minus 2. Okay. Just kind of going back to our calculator for a moment, though. You know, the calculator spit out for us, fortunately, the y value we wanted. But let's say, for instance, that they wanted point P up here, which means we would have been closer to, say, 8 or 9. How would we have found that y value? Well, we'll still use the solver, so I'm going to go back and grab that. But if you know your answer should be, say, closer to 8 or 9, after your comma y, you can put in a comma 8. You're telling the calculator where to go look. If I knew it was that third point up there, which looks like it's closer to, say, 10, I could have used the solver and then put in a 10, and it gives me my y value there. So just because it spit out the first number that we wanted doesn't mean we can't go find the other ones. Okay? All right, let's take a look at part B. It says for y less than or equal to 11, find the y-coordinate of each point on the graph where the line tangent to the graph at that point is vertical. We've talked a lot about horizontal tangent lines, but now they're asking about vertical ones. So let's go look at our graph here for a second. Let me erase this. Talk about vertical tangent lines. It'd be where your spaghetti is standing straight up. So I think that would happen here. And the good news is it looks like it's symmetric. So I'd say that there's one y value there. I'd say it looks like it happens again out here. So I'd say probably around 6 something. And I'd say somewhere in here, like very close to maybe 1/2. So I'm going to jot that down. Y equals 1/2. Y equals, what did I say, like 6-ish. And then this other one is, let's say, like 9 something. So just by looking at the picture, we know where that should happen. And I say that because I think it's going to help us with solving our equations. Okay. All right. Something we saw you know, a lot was talking about when is the tangent line horizontal, and we said that's when the slope is equal to 0. Well, if we're talking about vertical lines, you know, we've always said that means the slope is undefined. Well, what does it mean to have undefined slope? Well, let's take a look at it mathematically. If this is the point like, I don't know, 1, 5, this is the point like, you know, 117. We'd say, well, the slope would be up 12 and over 0. And that was the undefined part, is that we were dividing by 0. So for us, we're saying when you find the slope, the denominator will be equal to 0. Great news. Here's our derivative. Let's go write this down. If we want a vertical tangent line, then we're looking to see when the denominator of the slope is equal to 0. So let's go solve for y. 1 minus 5 sine of y equals 0. I say we use the solver again. We kind of know already where our answer should be. So I'm going to go back to my solver, menu 3.1, and I'm going to type in 1 minus 5 sine of y equals 0, comma, y. And let's see which one it spits out. So the first one it spits out is what I called like 1/2, which is 0.201. Let's go write that down. y equals 0.201. There's my first answer. We know there's one kind of around 6, so let's go back to the solver and then say comma 6. Perfect, 6.484. So we got that one, and now we know there should be one more, which is close to 9. So let's go back to that solver and change that 6 to a 9, and we get 9.223. It certainly helped that we had the graph, because it allowed us to use the solver to find, what we knew was going on for both of these parts. We certainly could have solved these equations on a graph. I think it kind of opens up a can of worms, because when we go to graph, we have to use x's, and we just have to be careful, that's all. But I like the solver if we kind of know what our answers should be.